So we're now in a new chapter. Chapter 5 was all about equations and solving. Now we're going to talk about inverse functions and something called one-to-one. And so we've got a couple definitions here and just some basic algebra skills. I'm trying to look to see a lot of, is nothing too difficult, nothing that can't be done that you should find much easier than the last chapter for this one. All right, so there is something called a horizontal line test. And what that horizontal line test does is that a function is considered one-to-one. One-to-one. If every horizontal line intersects the graph of the function at most once. So in math, we like our functions to be one-to-one. That means for every x, I have an output y. It's a one-to-one function. Okay, there's not multiple versions of y's. Normally, your x's can't repeat, but your y's can. Now we don't want really anything to repeat. And so what happens is the horizontal line test does that for us. The horizontal line test actually proves or helps us prove if a function is one-to-one. So remember, doing a vertical line test proved that if it was a function, a one-to-one will prove if it, a horizontal line will prove if it's one-to-one, excuse me. So I've given you some pictures here, and really all you have to do is kind of draw a horizontal line like you would do a vertical line and see if it crosses the graph once. So if I draw a horizontal line through this parabola, oh man, it hits twice. So this is not one-to-one. This one, your little cubic one, if I draw a horizontal line, it hits once. How about here it hits once, here it hits once? Yeah, this one is, yes, it is one-to-one. This one doesn't hit, only hits once. Remember, there's an asymptote here, but really you're only hitting once. You're only hitting once. So yes, this is also one-to-one. Okay, so as long as you draw horizontal lines on the function is one-to-one. So some easy questions right there in the beginning to answer when you're doing 6.1 homework. It's just graphs and you just do a horizontal line test. All right, now a function is one-to-one if for elements A and B from the domain of F, if elements A and B from the domain of F, A cannot equal B implies that F of A cannot equal F of B. And again, all they're saying is you don't want to have multiple X's and multiple Y's. You don't want them to be equal. You want them to be different, okay? So I wanted you to just write that little extra idea of what it means to be one-to-one. And then another part of homework tonight, they're going to give you these equations and they're going to say, okay, is it one-to-one? Well, this is as simple as putting it in Desmos and just doing a horizontal line test on it. So like for this first one right here, 2x plus 7, we'll go to Desmos and we'll put it in. You all should know what it looks like. 2x plus 7. It's linear. Can I draw a horizontal line and it only crosses once? You betcha. So this one is, yes, it's one-to-one. And you do that for all of these, okay? This one, you know, is a parabola, and parabolas are not one-to-one. Look up here. Parabolas are not one-to-one. Okay. This one is a square root. And if you remember what this one looks like, again, you can put it into Desmos, but it goes to the left 5 and it shifts over. Well, that actually, if you do a horizontal line, it will only cross once. So yes, this is one-to-one. And then this one is your cubic function, and x cubed plus 5x minus 3. And again, let's just put that into Desmos. X cubed plus 5x minus 3. Okay. So this cubic function is 1-to-1. If it was one that was really exaggerated, it wouldn't be, but this one is definitely a 1-to-1 function. So, all right, a few more definitions, and I know it seems weird why these definitions are in here, but it will actually help you for some things we have in the future, some things that they say actually on Pearson, if I remember correctly. All right, now there's this idea of inverses. So we just learned about what it means to be 1-to-1, but now we're going to find out what it means to be an inverse. Okay. For a function to have an inverse, it must be 1-to-1. It must be 1-to-1. If you want a function to have an inverse, it has to be a 1-to-1 function. The domain of your function will now become the range of this notation is inverse notation. F to a -1 does not mean F to a -1. It means it's just inverse notation for the inverse of a function. But the domain of the function becomes the range of the inverse. And I think I messed this up here. Yeah, I did. That's all right. This one is supposed to be, look at me typing and I messed it up. That's okay. Let's go like that. There we go. Switch that real quick for me. The domain of f is the range of the function, and the range of f, that's supposed to be an f, sorry about that, is now the domain of the inverse. So they switch. Your domain and your range literally switch for inverses. So kind of neat. If the coordinate AB is on F, then BA is on the inverse. They are reflections of each other and they reflect across the y equals x line. Okay, so this is all information about inverses, and we're going to do examples of this so it'll make more sense for you. So don't worry about it. And then if two functions, if I tell you that two functions are inverses of each other, if I say f and g are inverses of each other, then the fog, if you remember how to do f of the g, if you fog them and it equals x, and you goff them, it will equal x. Why does it equal x? Because they're going to flip over that y equals x line. So that's what makes them inverses of each other. All right, so a couple things right here. If you are an inverse, you must be 1-to-1. The domain of the original function f is now the range of the inverse. The range of the original function is now the domain. The range of the original function is now the domain of the inverse. If you are a coordinate AB on the original function, you are now the coordinate BA on the inverse. And you're reflecting over the y equals x line. And then if two functions are inverses, you should be able to fog them and goff them, and they'll equal x. This is the stuff that we'll keep referring back to for the next few questions right here, right? So hopefully you got that in there. So let's see what the first question is right here. Our f of x equals x cubed minus 1 and g of x equals the cube root of x plus 1 inverses. So this is that last statement that I just wrote on the previous page. If you have two functions and you want to find out if they're inverses, you just have to fog them. And if it equals x, then it works out, or golf them. Now, if you remember what fog means, you take the g and you plug it into the f everywhere you see an x. I'm going to take this function and plug it in right there for x, and I'm going to rewrite that equation. This is the f of the g of x. So the f function right there for x, I would now write the cube root of x plus 1. That's my x, but now I'm cubing it. and then minus 1. Well, when I cube root and when I cube a cube root, they cancel. And I'm left with x plus 1 minus 1. Well, that cancels. And look what I'm left with, x. If you are left with x, then yes, they are inverses of each other. That's all you have to do. If they give you an f of x and a g of x and they ask you, are they inverses of each other? Fog them or golf them, whichever one you feel comfortable with. And if they equal x, you're good to go. Okay, this was another question on homework, and it said, determine whether each function is one-to-one and determine its inverse. Okay, so to be a function, your x's can't repeat. To be one-to-one, your y's can't repeat. Don't let your y's can't repeat. Write that down. So if I'm looking through my list right now, just double checking, looks like I got some y's repeating a couple times, actually, 2 and 2, and then 1 and 1. So no, this is not one-to-one. This one right here, I'm going through 3, 1. I don't look like I'm repeating any of my y's. Looks like my x's are good. It's a function. So now that this is one-to-one, if it is one-to-one, you have to determine its inverse. Well, this is really easy. You go like this. You write g to the -1, which just means the inverse of g. And you take each coordinate and you flip it. You literally flip the domain and range. You flip the x and the y. So instead of the point 31, 1, 3. Instead of the point 02, 2, 0. Instead of 2, 3, 3, 2. 4, 0, 0, 4. And there you go. That's your inverse right there. Done. Easy peasy. So check a couple things. Check to make sure the y's don't repeat. And then if they don't repeat, then check to see that all you have to do actually is just switch your x and y, and that's your inverse. Okay. The next part will be finding actual equations of and their inverses, the inverses equations. And so we're going to do some of these right now so you can see what I'm talking about. All right, so to find equations of inverses, it's actually very easy. All you have to do is switch your x and y and solve for y. Switch your x and y and solve for y. Now remember, f of x is just a fancy notation for y. So we're going to call this x, and the x we're going to call y. So all I did was just switch my x and my y. Now I'm going to solve for y. Well, that's pretty easy. I'm minus 5 over, and then I divide by 2. This side right here is now my inverse. My inverse function would be x minus 5 over 2. And again, you can plug this into Desmos, and just to show you what it looks like, here's your original function, 2x plus 5. Here is x minus 5 over 2. These two functions are inverse. If I actually graph the y equals x line, they should be able to flip over it, which they do. If I were to fold along this black line right here, this purple line would land on top of the green line. And so that's how you know you did it right. If you put them into Desmos and they look like they're flipping over this line right here in the middle, this y equals x line, which they are, they flip right over it. Let's do another one. I saw them do this on Pearson. F of x equals x squared plus 2. Well, x squared plus 2 is a parabola that's been shifted up 2. And parabolas fail the horizontal line test. It's not one-to-one. So you don't even have to find it. Does not have an inverse. We could restrict the domain and give it an inverse, but I only saw that on one question, which I gave in a future example. So we'll do that in a minute. All right, this one, x minus 2 cubed. We're going to, this one is one-to-one. So we're going to switch our x and y and solve for y. X equals y minus 2 cubed. Okay, so again, got to get y by itself. How do I undo a cube? I cube root it. So take the cube root of this side and the cube root of this side. On the left, you'll have cube root of x. Cube root and cube will cancel. And you're left with y minus 2. And then again, you're just solving for y, so just add 2 over. Cube root of x plus 2 equals, and I'm not going to put y, I'm just going to put the inverse. And I think it's always important, let's just, double check here, make sure that we did it right. I like to always look at the graph of it. Let me go to Desmos. I'm going to put in the original. Well, I'm going to keep this y equals x line because I want it to flip over that. So I'm going to put in the original, which was x minus 2 to the power of 3. And then what I got was the cube root, which really is x to the 1/3. And I'm going to add 2 to that. And look at that. That looks to me pretty good, actually. Like it is flipping over that black line. If I were to fold, I know it's hard, but think about me taking my computer screen right now and I would fold right along this black line. That would be my fold. This red line would land on top of this blue line. And you can look at some of the points right here also that would help you out. Let's see if it gives us a nice point. I think there's, whoops. Like this is a point right here, 2, 0. Let me see if flip that, 0, 2, is that over here? Look at there it is, 0, 2. You have to have a point. I think there's a point at 4 if I'm correct. Oh, they're really being accurate here. But you just want to make sure that these points are flipped. And they're pretty much flipped versions of each other. So that looks really good. And you can see that you did it correctly. Righty? All right, yes. Now this one, these rational ones, which we did a whole lovely chapter on them. The function 6 over x minus 7. Okay, so we're going to find the inverse of it. And then I do want to talk about domain and range and all that first of it. Okay, so let me graph this first into Desmos. So 6 over x minus 7. There we go. We got a horizontal asymptote, and we should all know where that horizontal asymptote is. There's a horizontal one at 0. There's a vertical asymptote whenever the denominator equals 0, which would be at 7. So when we're talking about domain, we need to include that 7 as a restriction in the domain. For the range, we need to include the horizontal asymptote. Let me go back. And I am going to graph this one just so you can kind of understand what I'm talking about here for domain and range. So I have the vertical asymptote is at 7. 1, 2, 3, 4, 5, 6, 7. And the horizontal asymptote is at the 0. And then I have a hook here and a hook here. And this is my original function. So if I were to ask you what's the domain of f, you would say, okay, from negative infinity up until that asymptote at 7, united with 7 to infinity. The range, how tall is this? You'd say, okay, from negative infinity up to 0, though. United with 0 to infinity. Well, according to inverses, what we wrote on that first page, if I did this correctly, okay, my domain of the function will now become the range of the inverse. And my range of the function will now become my domain. If you do it correctly, those flip-flop. Okay, so let's actually write the equation and see if we do it correctly. So once again, I'm going to call this x. I'm going to call the x value that I see y. And I'm going to solve for y. And the quickest way that I do any fraction is I put this over 1 and I crisscross like that. So x times y minus 7 would be xy minus 7x equals 6 times 1 is 6. And again, remember you're solving for y. So let's add the 7x over. 7x plus 6. And then divide by x. So y, which is really the inverse now, equals 7x plus 6 over x. Well, let's graph that and see if I flip-flopped my domain, if I flip-flopped my range. So 7x plus 6 divided by x. Okay, so now I'm looking at this purple equation. And it looks like I now have a vertical asymptote at 0. And it looks like I've got a horizontal, yes, a horizontal asymptote at 7. And that makes sense too, based on degrees. We know that for sure. And again, you could put this y equals x line right here. And they are crisscrossing, they are flipping over that y equals x line, which looks crazy. But they are definitely doing that. So let me show you what I have again. Let me kind of draw it out for you. Whoops, wrong one. Okay, so on this new graph that I have, I now have a asymptote, a vertical asymptote at 0. And I had a horizontal asymptote at 7. 3, 4, 5, 6, 7. Oh, I'm way off the page, but. And then my hook was here. And my other hook was here. And if I were to write the domain of my inverse, which is my green function, I would say from negative infinity up to 0, which is exactly the flip-flop of the range. And the range, how tall is this green line? Well, it's from negative infinity up to 7 now. Hey, that's the flip-flop of that. So just something, again, to be aware of in the back of your mind. The domain of the original now becomes the range of the inverse. The range of the original becomes the domain. And if you did it right, it will work out that way. all the time. All right, one more of these. And then we're almost done. Yeah, easy peasy. Yes, they love this one. Let me make sure we know how to do this. I'm not going to graph it. I'm going to safely assume we can figure out domain and range. Again, domain is restricted from your denominator. So my domain would be from negative infinity up to 4, unite with 4 to infinity. You can plug it into Desmos if you don't trust me. The range is based off of the horizontal asymptote, which is at 2. So it would be from negative infinity to 2. And then 2 to infinity. And then again, if you just switch these and those, that's going to be the inverse. And you know you did it right if you can just switch these. This would now, the domain of the inverse would now go from negative infinity to 2 to infinity. The range would now go from negative infinity to 4. And now we're going to figure it out. We're going to actually find the equation that does that for us. So let's go back up here. Sorry, it's so tiny. I should have made it larger. Again, make this side X. Everywhere you see an X, make it a Y. Don't worry about this. This is just a domain restriction saying X can't be 4, which we know that it can't be 4. It's an asymptote. Put this over 1. You're going to crisscross multiply just like I did the other one above it. X times Y minus 4 would be XY minus 4X. 1 times 2Y plus 7 is 2Y plus 7. Now, you have multiple Y's here. So you want to get all your Y's on one side and everything else that doesn't have a Y to the other side. So this Y, I'm going to move over to that side, and this 4X I'm going to move. So I'm pretty much switching these two spots. So XY, I'm going to minus the 2Y over. I'm going to add the 4X over to that side. And then there's a trick in math if you want to get Y by itself, but you have like these, other variables in front of it, you can actually factor out a Y. If you did, you'd be left with X minus 2. And now you've got Y by itself, so you can get rid of that by dividing it out. And that is the inverse. 4X plus 7 over X minus 2. And look what happened. The denominator is your vertical asymptote for the domain, which is at 2, and that's what I wrote over here. 2 was my vertical asymptote for my domain of my inverse. 4 is now the horizontal asymptote, and that would be part of the range. So you know I did it correct. This bottom can't be 2, by the way. But this is how you could, again, you can double check anything, put it into Desmos, put this into Desmos, put this into Desmos, see if it flips over the Y equals X line. But this is all doing it analytically and algebraically. All right, last and final few things. They gave you this F function and they put some dots on there. And then they said, okay, well, find the inverse at 3, okay? So here's what I would do. If this is the function F that they're telling me, and I want to find the inverse, I'm going to find each one of these coordinates and then I'm going to flip them. And then I'm going to be able to find the inverse of it. So, and of course my computer didn't really graph it well for me, but there's supposed to be some marks here. But this is the point 0, 3. And this point right here is -5, -3, just so you know. And this is the point 3, 4. So if I made a little table here, my x and my f of x, I would have -5, -3, 0, 3, and 3, 4. Well, if you want to draw the inverse, you literally just flip those two. The inverse would be, instead of -5, -3, it would be -3, -5. Instead of 0, 3, it would be 3, 0. And instead of 3, 4, it would be 4, 3. And, you can graph it if you want to, but we're asked to find the inverse when x is 3. This is my x. Sorry, this is my inverse of x. So when x is 3, my answer would be 0. And again, you can plot these. 1, 2, 3 would be about here. 4, 3 would be right about here. And -3 would be down here. This looks terrible because that's supposed to flip over that line. I don't have any extra lines. I need to make that graph a little bit darker, but that's how easy it is to do. Literally take the points they give you, flip them, and then answer the question. This is your x. So when the x is 3, your inverse is 0. It's very simple. Last one I saw this is this idea of restricting domains, which can happen, and it really only happens with parabolas, because parabolas, unfortunately, they're not one-to-one, that you can draw a horizontal line and they don't work. So this one, again, you can put it in Desmos, but we all know what this looks like. This is an upside down parabola that has been shifted up 1. It goes like that. Well, if I wanted to make it one-to-one, I would just want half the parabola. If I just restrict the domain to half of it, then I can create a one-to-one function, meaning if I just get rid of this portion right here and just use this portion, I can actually find an inverse. So I can restrict my domain to be from 0 to positive infinity on the x. Then I would be able to find domain. Now, could I do this side too? Sure, you could. But you just have to, pick one of the sides. I can't remember how they ask it in that might be a multiple choice question, but you just have to just pick a side and you just cover up this side. This would be negative infinity to 0, or you could restrict the domain from 0 to infinity. And then you have a one-to-one function. Much easier to do. All right, so that is it for one-to-one and inverses. Hopefully that made a little bit more sense. I know it was a lot of big words in the beginning.